Let me introduce our speaker. So Professor Gene Turner is a distinguished professor in the Department of Physics and Astronomy at the University of California at Los Angeles. Professor Turner is one of the world leaders in studying star formation, chemistry, and the birth of star clusters. So with her students and collaborators, she's used radio and millimeter wave interferometers to observe the hidden nuclei of galaxies and forming star clusters in nearby starburst galaxies. So in addition to pushing the VLA to its limits and carrying out pioneering studies of chemistry in galaxies, Professor Turner has been heavily involved with ALMA since its earliest days. Recently, she's been doing groundbreaking work pushing ALMA to its limits to observe the birth of star clusters, which she'll tell us about today in her talk, Gas in Young Superstar Clusters. So without further ado, I turn control over to Professor Turner.
Thank you very much, Adam, for that lovely introduction. And so I'm very honored to be asked to give a talk on a subject that I'm very passionate about, which is the formation of giant star clusters. And this is basically what subarcsecond imaging and spectroscopy can do for you in the radio and infrared. So the goal is to look for the very youngest star clusters and try to define their properties. I'll try to explain how these star clusters are a little different from what we're used to in the galaxy. We've made great progress in the past 40 or 50 years in understanding star formation in the galaxy. And why go to other galaxies? Well, it's because star formation elsewhere may be different. I think we have good evidence that this is true. So I'm going to talk about work that covers many years, actually, and includes the following people. Some of my students here listed, Michelle Consiglio, Daniel Cohen, and longtime collaborators Sarah Beck and Paul Ho, and some of you may know Nick Ferraro from the VLA, who's just starting. I'm also going to discuss some theoretical work because in this subject, there's a real interplay between theory and observation, and in the sense that I think the theorists predict what we end up seeing. So I'm very impressed with their work. Okay, so I'm going to start out with sort of why giant star clusters are particularly interesting. And let's see, I can advance, here we go. So I'm going to start with a schematic of the Milky Way, and this is sort of a rough schematic, sort of Astro 101, but it's going to be the 2020 version. And the 2020 version has a big halo, and this is a coronavirus halo. And I'm sorry, but it's on everyone's mind. It's affecting us all. And it's the thing that came to mind when I'm doing my schematic, but we'll get rid of it. Okay, so we'll fade it out. It's still there. There's a halo. So there's a halo to our galaxy and a lot of very large clusters. So the globular clusters in our galaxy are all very old. An interesting system. It's believed that the halo is mostly dissolved globular clusters. So what we're left with are the biggest. The masses are 10 to the 5th to 10 to the 6th. Some of the largest may actually be nuclei of accreted galaxies, that's unclear, but most of them are star clusters. And they formed at Z of 2 to 4. There are people who argue, Bruce Elmgreen has argued that if you sort of estimate how many of these clusters formed in the early universe, that it could have been a dominant mode of star formation was to form these really large clusters. And that has implications for things like starburst regulation, et cetera, as you will see. So they are a very important element of the assembly of galaxies. Okay, and one thing to point out is that these clusters are so large that if they had a typical IMF, you could expect 1,500 to 2,000 O stars in a small volume. So that's quite a star-forming environment. Now, the discovery of superstar clusters in the current universe, in local galaxies, and this is the galaxy, I think, in which it was first. I'm not sure if this was ARP Sandage and Arp wrote a paper in 1985, and they coined the term, I think, superstar cluster. It may have shown up earlier. It was one of the first uses of it. And these two big star clusters there are superstar clusters. Some of the questions about these large clusters that we have are efficiency. Do superstar clusters form more efficiently than galactic star forming regions? I think there's good evidence that they have to, because if you look, these are virialized systems. The globular clusters are virialized, and to form a virial system like that requires efficiencies of 30 to 50%. So 30% if gas is lost slowly over time from the cluster, or 50% if it's lost impulsively, like in a supernova event. So these things, in order to last, they have to have high efficiency. And this is not an efficiency that's seen in the Milky Way, typically. And in fact, we don't see very large clusters forming. We see much smaller star formation. There is a very large cluster, Arches. There are a couple of large clusters in the galactic center, and it could be that galactic centers form these, but we don't see them forming in the Milky Way. So we need to go to other galaxies. Another question is feedback. How do these multitudes of stars, including O stars, interact with their surroundings? And finally, a sort of relatively recent discovery that globular clusters have multiple generations. Well, I should say multiple populations, because this is something that's deduced chemically, but it's probably caused by multiple generations of star formations. If you have a large, dense cluster, how do you form multiple generations of stars? Very hostile star formation environment. Okay. So these are the basic questions that I have. All right, now I just want to point out for superstar clusters or concentrations of O stars, let's just look at what one O star can do at different phases of its short life. The first is up in the upper left corner. This is Deborah Shepard made this map of a bipolar outflow. So they have bipolar outflows when they're very young and forming, accreting. And then you have luminous blue variables like the homunculus in Eta Car, which, and I should point out that this circle in each case, in each diagram, it represents 1 parsec. And the cores of globular clusters can have radii of 3 parsecs or so. So this gives you an idea of how great the influence of a single O star can go. On the bottom left, we have a Wolf-Rayet star blowing off matter, and Wolf-Rayet stars are stars greater than, initial mass is greater than 25 solar masses, and they lose up to 2/3 of their mass in stellar winds. So this is an important evolutionary phase of an O star. And on the bottom right, of course, there's a supernova remnant. This is, I think it's Cas-A. It's buried beneath my Zoom window here. Yes, Cas-A. So a supernova remnant. And so these are all the different ways that O stars can be destructive. Now, imagine that you have 1,500 to 2,000 O stars in a volume that's 3 parsecs in radius. It's just, one can't imagine how hostile this environment is. Really different. Okay, so we're going to move on to my favorite source. This is an amazing object. It's NGC 5253. It's a blue compact dwarf galaxy because it has a giant H2 region in the center. But underlying it is a dwarf spheroidal galaxy, so that if you look at the stellar kinematics, they're dispersion dominated. So it's like a dwarf elliptical galaxy in a way. But it's got a lot of star formation. It has a very prominent dust lane, and it's close. It's less than 4 megaparsecs. It's a fantastic laboratory for studying the formation of superstar clusters. A little bit more background. The H1, now I'm not showing the VLA image of this. This is an H1, a low resolution H1 image from Australia that shows a tidal tail here. Now this is an isolated galaxy. It's not merging. So the star formation is not caused by a merger, but it has interacted with some H1 and there are tidal tails. So it's unclear exactly what has happened to the system. If you look, the high resolution VLA image by Kobylnicki and Skillman shows loops around it and filaments, including a filament along that dust lane. Okay, if we look at the stars, this is from Daniela Calzetti's paper of 2015. She's got earlier work on this too, 1997. Here are the star clusters. It's got many star clusters that's forming. So we went to look at this with the VLA, and this is what we saw. Now, underlying this image on the bottom right, so the green is VLA free emission. So this is the free emission from the H2 region. Underlying it is the image from HST. Red is 1.9 microns, blue is 1.1 microns. And you can, well, first of all, as a radio astronomer, I have to say it was very gratifying to me to see a VLA image make an HST image look blurry. In all fairness, I think these objects actually are somewhat extended. But you can see that there is a very embedded source that only shows up at 1.9 microns, and it's probably dust. So the cluster that's exciting this H2 region is deeply embedded and invisible. So one of my points is that all we know about this cluster is from the radio. And this image was made with PyTown. It has a 50 by, it's actually 90, that's a typo, 50 by 90 milliarc second beam, where we were able to show that this thing is 1 to 2 parsecs across. So, and we can infer the luminosity. The infrared and the radio luminosity show that this is 5 times 10 to the 8th solar luminosity. So 500 million solar luminosities within a radius of 1 to 2 parsecs. It's incredible. Okay, so this amazing H2 region. Next, the question was, what's the CO doing? So we asked this question, and this is a picture of Owens Valley, which no longer exists. It became Karma. It got shifted up the hill to a higher site, but this is the original Owens Valley that did a lot of the early work on extragalactic CO. And so our first work on this galaxy was with Owens Valley, and this is our first image, and it showed that the CO was outside the galaxy. First of all, this was very weak. The infrared luminosity of NGC 5253 is within hailing distance of M83, but it has 100 times less gas. So very little CO, and what CO there is outside the galaxy. So it has all of these clusters that are cataloged by people who study star clusters, young clusters. Yet most of the gas is outside the galaxy, including molecular gas. Now, I was a little concerned about this because this is like a 10 sigma result, and Nick Scoville said this is one of the ugliest maps he'd ever seen. So they gave us more time to make a prettier map, and this is what we saw. This is Dave Meyer led this. This is CO 2 to 1, and we could see it a little bit better, and you can see that the dust lane is still there. It lines along the dust lane. By the way, it's redshifted, so it's falling into the galaxy. And the cross marks the superstar cluster. So there is faint emission, which is called Cloud D, that's visible in CO2 to 1, but there's still not very much gas. We estimated there was about something like 1 million solar masses associated with this cluster. And it's a very luminous cluster. So it was already pointing to very high star formation efficiency. And then we did it at the SMA. We were tired of waiting for ALMA, so we did it at the SMA. CO3 to 2. I was not expecting to see CO3 to 2, and it's a whopping bright source. And it's bright not because there's a lot of gas there, but because it's hot. We still don't really know what the temperature is because CO3 to 2 doesn't give a good handle on the temperature. Most of the gas is still in this streamer that's falling in here. So this is the bulk of the gas. It's really traced very well by the two lower transitions trace the mass, but you can see the activity going on in CO3 to 2, and it falls along the dust line. It's just really clear that this streamer is part of this star formation picture. Okay, now we move to ALMA. What did ALMA see? So we need a nice picture of ALMA. And this was taken, I've got a date here, that's not the right day. It was 2011, the first day of early science at ALMA. And here's what we saw with ALMA. We still see the streamer, and this is pictured on top of an HST H-alpha picture. Here's the streamer. It breaks up into these 5 parsec scale clumps. This is a 0.3 arcsecond beam. Here's the center of the galaxy, and we will focus in later on what's going on right around the superstar cluster. But this is the environment it's forming in, and you can see an anti-correlation on this scale with H-alpha. That's not surprising. So there's high extinction. You expect at least 4 magnitudes or so if you have CO, and so you expect this. It was not surprising. So let's look at a tracer that doesn't suffer extinction, which is radio continuum. Now, radio continuum is much weaker. So this is one of our old maps that has a low angular resolution. It's 1 arcsecond beam. And you can see it's just beautifully correlated, beautifully. I mean, when we made this map back in the mid-90s, I could see all of these features in the map, and all of them are correlated with CO. So this is all star formation. The one exception is this supernova remnant, which goes away at 2 centimeters. So we knew this was a supernova remnant, we identified it, but there's a beautiful, beautiful correlation. So the H-alpha is much more sensitive tracer of H2 regions, but the radio continuum really gets through the extinction to the star formation, the embedded star formation. Okay, here's a close-up of that central region. And we call this cloud D1. This is the cloud associated with the superstar cluster. This cloud is much bigger off to the right, is a much bigger cloud. It has more mass, but it is redshifted. So it's a different cloud. It's redshifted with respect to the superstar cluster. Okay, the superstar cluster is lined up with this extinction lane. So this is H-alpha, and you can see sort of puffs. It looks like there may be things coming out, photons coming out or of this region. Okay, cloud D1. Cloud D1, just to give you an idea. Now this is a totally fake picture. I took the galactic globular cluster M15 and I scaled it to the scale of cloud D. So this is what you would see if you could see the underlying cluster. It's not completely fair because M15 is an evolved globular cluster. They sort of adjust, the core shrinks, they puff up in the outer parts. It's not a fair comparison, but just to give you an idea of how many stars are in there and what's going on within this tiny cloud, it's remarkable to think about. There is a bridge connecting these two that I'll mention a little bit later. Okay, so actually I should mention here, how do we know that this cloud is associated with the superstar cluster? There are 3 lines of reasoning. First, the CO is coincident projection. So they're very closely coincident, the radio continuum and the CO. The second, the velocity of the nebular lines seen like sulfur 4, CO, bracket alpha coincide within 2 kilometers per second. So they're coincident in velocity. And finally, the 13 CO measurements that I will show you strongly suggest that the cloud has been affected by the cluster. So here's the final piece of evidence. Here's 12 CO 3 to 2, 13 CO 3 to 2. The ratio is 40. Now the other clouds around have ratios of more like 7 to 9. You can compare that to 11 on Orion. Orion is optically thick in spite of the ratio of 11. Basically, you know, the 12CO arises in slightly different gas. And so this is the Orion is a survey by Peter Schielke, and he has many lines, and the lower J transitions too, and he knows that it's optically thick, so the arguments are there. So this is to compare to Orion. These clouds are Orion-like. This cloud is not. So D1 has definitely been affected by the cluster. Now the line profile. Line profile has a width of 22 kilometers per second, which is completely explained by the mass. And so this is in fact one of the best masses we have for a superstar cluster. It's about 4 times 10 to the 5th solar masses. That's gas plus stars. Okay, and here's the line profile here. And it's smooth. Now I will focus on this left side, which is the blue shifted side. The red shifted side, I will talk about in a minute, is affected by that filament. The blue shifted side is very, very smooth. And if you calculate how many sources, it depends a little on the intrinsic line width, which we don't know. If you assume it's 1 kilometer per second, you need hundreds of clumps to produce that line. If you have protostellar disks, it's maybe 50 clumps, but it's many, many clumps to produce a Gaussian line. If you look at W49 at a similar stage, it has a very complex CO line. So it has structure, and it's formed by filaments. This one's not. This one's a much more Gaussian-like line. On this side, you can actually see the influence of that filament. We think it is, people suggest maybe it's rotation across the cluster. We actually think it's that connection to that cloud in the southwest. So it could still be accreting gas. Okay, the very relatively small mass given the luminosity suggests a top-heavy IMF. This depends on the stellar models, so it's a little uncertain, but it seems to be top-heavy. And if stars are still forming there, they will be massive. So if you calculate the Bonner-Ebert mass, which depends on the temperature and the pressure, it's 10 solar masses for 300-degree gas. So we will know more when we get a good gas temperature. Okay, and this is just to show you that the bracket alpha line, which is a little bit more, it's 4 microns, more so than H alpha, it gets through to the nebula. You see, again, a very smooth Gaussian. There's a little indication that there may be some sort of outflow. And this is more in the outer parts if you look outside the main superstar cluster. This is a helium line, by the way. It's not gas coming out. Okay. It's also dusty. So this is the final observational fact. Cloud D is dusty. Now this is based on the submillimeter array, not the ALMA. We've had trouble sort of subtracting off different bands, and it's tricky because there's so much free emission at 870 microns that you have to subtract. Subtracting is always tricky. I think Eric Murphy knows this very well. Trying to subtract non-thermal emission, subtracting 2 bands is tricky. But we've done it with the SMA. It's not subtle. About half the emission at 870 microns is dust. And so it appears to be dusty. And we would predict a dust to gas ratio for this inner 50 parsec region about 50. Okay, now this is a low metallicity galaxy. This is not what you expect. You expect 500. You don't expect supersolar. But this you expect. If you have a cluster like this, it's producing metals, it could produce dust. Now, just because it produces metals and have Wolf-Rayet stars and blows off the gas, enriched gas, doesn't mean you'll form dust, but it's plausible. So if you see dusty galaxies of ZS7, this is how it happens. It's Wolf-Rayet stars. So it's massive stars. Okay, now the final 3 slides before the conclusions. I just want to show you some theory. And this is the theory done by the group in Puebla. This is Sergei Silich, who realized in 2004 that enrichment by a massive cluster can actually affect wind development. And this was the best slide I could show. This is actually a plot of T versus R within the cluster. So it's not really showing you the development of a wind, but it's showing you the effect on temperature, which tells you about cooling. And the left is a model of Arches. So Arches is a smaller cluster. It's an order of magnitude or so smaller. Maybe it's less than that, something like that. And the solid lines are adiabatic solutions to gas flow. And the dashed lines are with cooling. So they're numerical solutions with cooling. Now on the right, they've modeled NGC 5253. They were taking a mass then of 10 to the 6th solar masses. So just a difference of an order of magnitude or so, and an increase in the metallicity to 1.5 solar. We can see that's entirely plausible based on the observations, can do this much to the cooling. So you get radiative effects from the enrichment from 2000 O stars, and it happens within 3 or 4 mega years. Okay, this is some more. This is from Tenorio Tagle et al. 2015. If you have supernovae that go off in the center, and if you have any mass segregation, and your most massive stars will be in the center, then you can slow the development of the supernova remnant to 0. So the lines, the solid, dotted and dashed lines are 3,000, 5,000, 7,000, the supernova remnant moving out. So if you form one away from the center, it can break out. But if you form one in the center, it can be trapped. So you can trap supernova remnants. And finally, you might expect to get, instead of mergers and a cluster wind forming, which I think a lot of people expected from these massive clusters, gravity is important. You can actually get a wind coming off from the cluster itself. But in this case, they're acting like individual H2 regions. That's exactly what we see with the Gaussian line, individual H2 regions. So in fact, this has ramifications for leakage, photon leakage. If things are confined, you can actually have stars that have become visible or managed to blow off somehow. You could get leakage of photons from this very clumpy structure. Okay, so this is what we have learned about this amazing cluster. It's optically obscured, and so the cluster cannot be seen. Record star formation efficiency, we will know more. We don't have a good gas mass yet. We're working on that. That's really tough because the CO conversion factor in this environment is tricky, and the line width is really dominated by the star cluster. So we have optically thin emission. When we have a temperature, we'll get a gas mass. So this is tricky. It's very hard. Filament fueled star formation, it could be. Most of the gas mass is outside this galaxy, not inside it. So it's a very curious environment. Optically thin CO, so not much gas. The CO3-2 is very bright because it's hot, not because there's a lot of gas. The line profile suggests that the molecular gas is not being blown out of the cluster. It also indicates collection of up to hundreds of individual cores in H2 regions. There's a possibility of a top-heavy IMF and a possible reason for it, that if star formation continues within this cluster, it's going to be massive stars. It has to be massive stars. And there's evidence for localized dust pollution. So all of this needs to be confirmed, in particular the dust. We're hoping to get some ALMA observations of that to confirm the dust and maybe get a temperature for the CO, maybe a mass. So there's more work to be done. Now, for future work, I'd really like to make the point that almost everything we know about this superstar cluster is either from the VLA or ALMA, because the cluster's invisible. And the luminosity, the mass, the kinematics, all of this that we have learned has been from the VLA and ALMA. And so they've been very important instruments for any future studies of similar objects. And it's not a surprise. This is a star-forming region, and it's true in general. And in terms of the NGVLA, higher sensitivity and spatial resolution will allow us to do more extragalactic work. And if we can extend our reach to 50 megaparsecs, if we go even to 20 megaparsecs, we can potentially get 150 to 200 of these objects. If we can go to 50, we can get many more. And so it's hard to infer things from a single object, much better to go to samples. Okay, so there's still a lot to be done. I think the future is very bright with data from ALMA and the VLA. The VLA, especially with the improvement in sensitivity at the higher bands, is a very important player in this. The NGVLA would be amazing. So that's FEAM. Thank you for your attention.
Thank you, Jean. That was really amazing, fantastic observations and a really incredible object. So we have a bunch of questions and more quickly rolling in here. So the first one comes from Mark Gorski, who asks if there's an X-ray detection of the cluster and if there's any evidence for a buried AGN in this thing.
Oh, okay. X-ray detection, yes. There's soft X-rays. I think Rob Kennicut and Crystal Martin did it, but it's also been redone by Chandra. And I'm blanking on who did it, but yes, there's X-rays. And we think it's coming from the hot gas. As far as evidence for an AGN, you saw that CO line profile, and there is no kinematic evidence for an AGN. You know, so I don't know what to say. I mean, how would you detect an AGN? There's hard X-rays, no, it's soft. So there are hard X-ray sources. I think they're X-ray binaries. They're not at the superstar cluster, no.
Got it. So there are also some questions about more details on these top-heavy IMFs. So in particular, there's a question asking whether you could go into more detail on evidence for the top-heavy IMFs and currently to tell us about what constraints there are currently on just how top-heavy the IMF could be in these superstar clusters.
Okay, well, we've slightly revised the mass of the cluster because Sergei Silic pointed out that I used a 1/x profile and got something like 2 to 3 times 10 to the 5th solar masses, and he points out it should be more, you know, he's done an sort of a Gaussian profile consistent with the Gaussian line profile. So the 4 times 10 to the 5th is a good number. Of course, the problem is, there are two problems with coming up with an idea of the lower cutoff. First, you need an upper cutoff, okay? And I've been using Starburst 99, and I think the upper star they put in there is 120 solar masses, so that's one thing. It depends on the stellar models. I have tried every stellar model there is in Starburst 99. They all give, you know, top-heavy IMFs, all of them. The other problem, of course, is that our mass includes gas. And our gas estimates have ranged from 6,000 to 60,000 solar masses for gas within the cluster. And since the cluster itself is 4 times 10 to the 5th solar masses, the 60,000 solar masses, you know, could contribute to the mass. So we don't know the mass of gas. That's one of the problems. So and also the age of the cluster, and that comes in too. If it's really, really young, then you get more ionizing photons out, and that's one of the important constraints. So there are many unknowns. But every model I have tried that works is at least 1 solar mass, lower cutoff.
Great. Could I ask a quick follow-up question? If you took a normal IMF with the free observation that you measure, what's the implication for the amount of gas that's there? Does it just not work with the CO emission?
If I take the normal free with the amount of gas there, I'm not understanding the question.
If you assumed that the IMF was normal with the ionizing photon flux that you measure and subtract it from your dynamical mass, what's the implication for the leftovers?
If what you're saying is, okay, if I assume a normal IMF, I can't fit. I am assuming all of that 4 times 10 to the 5th is stars, and I can't fit it. I can't fit the ionizing photons with that. It's potentially, if it's 1 million years old, maybe. So I think there's some area to explore there in trying to figure out how young the cluster is through some sort of leaking photons, you know, in spectra, I don't know. So there's work to be done there, but the evidence right now is that it's top heavy.
So there's a lot of interest in knowing if JWST could provide more clarity on the nature of the cluster. So whether JWST can help answer this.
Maybe. We have done observations in the mid-infrared, sulfur 4, of the cluster. JWST could perhaps do better. There's H2. You could, you know, H2 could tell you something about the gas content. The beauty of H2, of course, and does it get to H2? I know it gets to H2. I know it's not very sensitive. That would be the thing to do, would be H2, because then you don't run into chemical problems. I mean, Adam knows all about this. Adam and Alberto know about this. There are chemical problems, you know, that if you're trying to infer a mass from CO, you have to assume an abundance ratio. In an environment like this, it's tricky. It's really tricky. So it would be great to have H2, for sure. The extinction's very high, and so I think you see, I'm not sure that JWST, it could maybe tell you something about the nebula and the excitation, which would be interesting. That tell you about the stars inside.
That's great. So there's also interest in this H1 cloud that's encountered the galaxy, and how much this is a unique situation versus maybe generalizable to the globular clusters, like how this whole scenario relates to other superstar clusters in other galaxies.
Oh, well, we're wondering if it's filament fed. We have a CO3 to 2 map of HE210 too, and that's a fascinating object in its own right. Another dwarf galaxy with filaments coming into it. This is okay. The other thing about this galaxy, about NGC 5253, and potentially the other dwarf galaxies in which we see these things, is that they're dark matter dominated. It's really hard to tell where the mass is. So I've tried to compute an acceleration for the streamer, but I don't know where the mass is or how much mass there is there, because it's probably got a lot of dark matter and its dispersion dominated. It's kind of hard to tell. There are streamers coming into this thing. We think it's filament fed accretion. The thing about a globular cluster is that you kind of expect that something that massive will form if you don't have a lot of angular momentum, because angular momentum, you know, kind of spreads things out and makes collapse more difficult. And so it's hard to picture forming such a compact cluster if you have a lot of angular momentum, a lot. So if you have intersecting streams, you might expect that that's more favorable. And I think there's some evidence actually in galactic star forming regions now that you have streams coming in. The other comment I'd like to make is that I think the high efficiency could also be if you have a destination target for your gas. So this is not like some big molecular cloud in the disk of a spiral galaxy that has turbulence, and every once in a while, you know, something decides to, it gets prodded and starts to collapse. This is the case where you have a streamer that has coming in along the galactic potential, and it's coming in, it's raining in. It's similar to a galactic center. I always wondered in spiral galaxies where you have to drift inward of gas, there's one place that gas is going to end up, it's the galactic center. So there is, it's called the conveyor belt model of star formation, where you get higher efficiency where you have a conveyor belt. And this streamer is like a conveyor belt coming in. So I kind of wonder if that isn't related to it too. So that's a question. We need more galaxies to sort of study that question well. It's a good question.
That's great. And I think that also addressed, there was another question on the conditions that you think led to this very high star formation efficiency. So I think that also directly addressed that. So we have another question on, so you're talking about the stalling of common modes of feedback, and there's another question asking how long star formation could last. Like, what's the upper bound for how long this could go on inside this cluster?
Well, that's a really, really good question too. I think that it's hard to answer. Well, first of all, there's an important point. People talk about ages of clusters, and this is something that Sergei Silic really gets worked up about, because there is a time scale over which star formation takes place within a cluster. If you're talking about a 1 to 3 mega-year cluster, and it takes 1 to 3, it takes of order a mega-year to form a star, they're not instantaneous objects anymore. When they're this young, you have to worry about the time scale of star formation. As for how long it takes place, I think this is something we'll have to do observationally. Now, there are people, I think, who've done studies of, clusters and visible clusters and their ages, and I think it seems to be maybe 4 or 5 megayears. I don't know if that's true for these really huge clusters. And in fact, you kind of wonder if this isn't the way a nuclear cluster gets started in a galaxy or something. It's possible that the largest objects just can take off, get really embedded, and if you have the right situation, they can take off. So this is something I think that will be answered with more observations.
So there's also a question about again, coming back to this emerging H1 cloud, there's a question about how well the metallicity is constrained in the gas across the galaxy, and whether that gives any evidence related to the nature of the interaction with the H1 cloud and any past merger or tidal interaction, and whether that might hint at the presence of any dark gas.
Oh, yes. Okay. Well, yeah, these are all really good questions. Really good. The only metallicity measurements I know of are in the nuclear region right around. They're very much affected by this superstar cluster, so they're nebular lines. That's a very interesting question about merger. Because this object is so strange that honestly you wonder what on earth it could be. There's the localized, if we see a localized peak near the superstar cluster in metallicity, which we think we do, we need to verify this with ALMA observations, get the dust. If it's supersolar there, it's probably due to the cluster. So I don't think we could tell if it's a merger. Now, the overall galaxy itself is 0.25 solar, times solar. It's 0.25 solar. I will say that we've done another galaxy with ALMA, Tuzuki 40, where we determined a gas to dust ratio for a cluster near H2 regions and off by itself. And there's a real difference that we could see in the CO3 to 2 to dust ratio if we interpret that as gas to dust. So there is evidence that these things are polluting. I think we need more information. We need better dust fluxes on higher resolution observations with ALMA, which is hard to do. It's high frequency work. So I think assuming a global metallicity for a galaxy is dangerous. That's my view. But I think we need more work to show that that's the case.
Great. So there's also a question about just how common, and I think this is related to the last few also, just how common these superstar clusters are. And the question asks, especially, would you expect these things to be common given the rarity of H1 streaming into a galaxy? Does that account for all of the superstar clusters that we see. Again, that's sort of a few of them.
Well, okay. I think this is, it's a good question. Adam, you've studied the star clusters in NGC 50 in NGC 253, which are somewhat smaller. There is a radio source in the nucleus, which I personally think is an AGN that might be comparable to NGC 5253, but I think that one doesn't have an infrared source. They show up in dwarf galaxies. That antennae have a whole slew of clusters. Now, again, the problem is the masses for these things. I kind of wonder about. You have to be careful about the masses. Some of the masses in the literature that have been quoted, I've looked at them. They're way too high. So you have to be very careful about the masses. This is why I'm very proud of this mass for 5253. And I think ALMA could really do a lot to determine masses for these young things. As to how common they are, in the local universe, they're not all that common. These really massive clusters, like getting close to 10 to the 6th solar masses, are not all that common. M82, it's been claimed there's a 10 to the 7th. I would say it's more like 10 to the 5th cluster there. So that's a hard question to answer right now. I think there's more work. It's an active area. There's more work that needs to be done. In the antennae, there is a power law distribution, so there are many lower mass clusters. And it's believed that our globular cluster system, the Milky Way, may have started out power law, and that the less massive clusters, through tidal shocking and things, dissolve. So it's probably a power law, but we'll see.
Cool, great. There's also a question about whether there's a prospect to observe fine structure lines from this galaxy, either currently with SOFIA or with some future infrared space telescope.
Herschel has done fine structure lines in this galaxy. I don't know specifically what, that it's fairly low resolution is the problem. We have looked, let's see, particular fine structure lines can.
This was not clarified in the question.
Okay, okay. This showed up, this was done with ISO. There were some lines like neon, I think those are fine. So neon 3, I think neon 5 shows up. Is that true? I'm not so familiar with this. It is a relatively high excitation H2 region. Let me just say that. It is in between AGNs and starbursts. So this object stood out as being unusual in that sense. So it's high, there's an indication of high excitation, yeah.
And that sort of brings us nicely to the last question, which is just whether there's any parallel between I'm paraphrasing here a little bit, but whether there's any parallel between the forming globular clusters that you see and the AGN region seen at the centers of galaxies.
Well, okay. I will tell a story. We wrote a VLA proposal. It was Paul Ho and Sarah Beck and I, and this was probably 20 years ago. We wrote a VLA proposal, and Paul Ho had decided this was an AGN, and Sarah Beck said, this is nonsense. This is an H2 region, and I was in between. I said it could be a supernova remnant. So we wrote this proposal and said, we're of 3 minds on this, and we got the time. It's really, really hard. This is a weird object. I mean, I wouldn't be surprised at anything. We see no evidence that it's an AGN. But here's the thing. If you get a massive enough cluster, I mean, this is a thing that these guys in Puebla, Silich, Tenorio Tagle, Roberto Turlovich, all of these people are sort of talking about this and thinking that if you get a big enough cluster and it self-pollutes and it stalls the feedback and you have a conveyor belt coming in, like cold stream accretion, which you expect in the early universe, then this is a way you could grow something really, really big, right? So this is why this object is so fascinating. Is it still accreting? Is it still forming stars? What's going to happen? Fascinating object. So that's why we're looking for the biggest objects, is how big do they get and what happens? So this is a fascinating theoretical result that's got me very interested, this fact that you can stall the feedback. And it could be going on in the early universe. So who knows? Who knows? Maybe it's the way nuclear star clusters got started, or maybe bigger. I don't know.
Great. It's really fantastic. And that brings us very nicely to almost right up to the hour. So everyone in there, all 170 people who've called in their dispersed location should clap for Jean. That was really amazing. Thank you.
Thank you, Adam. Thank you very much.